Check it out now, y'all.
NanoHub U, online instruction.
Well, welcome to the last module for this week. And if you remember, what we did for the first 4 modules was we worked with the expression for the conductivity in diffusive conductors. And what I tried to show is how you could adopt a specific model and have a way of calculating this density of states. And we use that to relate it to the Drude model for conductivity that is widely used. So that was kind of what we did for the first 4 modules this week. In the last module, we started with talking about this ballistic conductance, because one of the nice features of this way of describing transport, the one that we introduced last week, is that both the diffusive result and the ballistic result all fall out simply from the same viewpoint. And we had this expression for ballistic conductance, and what I said is, let's say if we write it in this form, with number of this quantity as number of modes m divided by h, what you can show is that m can be expressed in this form. That is, what we did was, we had this expression for total number of states up to a certain momentum p, and this is like the total number of m up to a certain momentum p. And what I tried to explain was how this represents like how many wavelengths fit into the box, while this represents how many wavelengths fit into the cross section. And from that viewpoint, I mean, if you just rearrange this a little bit, you obtain the expression I've put up here, which is m for 1 dimension is 1, 2 dimensions depends on how many wavelengths fit into the width, 3 dimensions, how many wavelengths fit into the cross section. And then I argued that these things in 2 dimensions and 3 dimensions, you'd think, would change continuously. That if I made the conductor wider and wider, this number should increase proportional to the width continuously. And in that case, you would expect that the ballistic conductance should also be proportional to the width. But once you adopt this wave viewpoint, that basically this is like the number of wavelengths that fit in, then this you have to take the integer value of this. So then you would expect that when you increase the width of something, the ballistic conductance should go in steps. That is, this m could be like 1 for a while, and then it becomes 2, and then it becomes 3, and 4, and 5, and so on, but does not go as like 4.7 or 5.8. It will go in steps. And this is the seminal experiment that was reported again a little over 20 years ago, back in 1988, which I have shown in that slide on the left. Actually, there were 2 separate groups that reported it around the same time, back in 88. And what it showed was an experiment which was done on a conductor whose width was continually changed. So you had this conductor whose width is W, length is L. The length itself is short enough that it's ballistic. In fact, these are what people call point contacts. These are extremely short. And the width is controlled by controlling the potential on the 2 sides, which we don't need to go into these details. But the way it was done is, by putting a voltage on the 2 sides, you could actually pinch in the channel or make it wider. So that's the x-axis. It's the width of the conductor. And if you look at the conductance is plotted in normalized units. Normalized in the sense that what is plotted there is this conductance divided by q squared over h. Actually, what's plotted is not conductance over q squared over h, but divided by 2q squared over h. And this 2 has to do with the 2 spins, which I'll come to in a minute. But Conductance is plotted, this normalized conductance, and what you see is it goes in steps. That is, goes from 1 to 2 to 3 to 4, etc. And the interpretation is that there's a two-dimensional conductor, so the relevant place to look at is this one. And ordinarily I might have thought that as I change W, the M should be changing continuously, but what it is doing is it's showing this integer, that it only goes with integer values, 1, 2, 3, etc. And that's what this experiment shows. And the reason we have the 2q square over h is because of what I had mentioned, I believe, a couple of modules back, namely that for any conductor, there's always these two spins, you see. There's an upspin and a downspin, which can be viewed as parallel channels. And so, it is like conductance. If you don't worry about spins, you calculate something. But then, there is an equivalent channel carrying the same amount of current, and so the conductances sort of add. The currents add, conductances add. And so, the conductance, if no spins were involved, then we would have expected that conductance normalized to q squared over h should go as 1, 2, 3. But then because of the spins, if you had normalized it to q squared over h, it would go as 2, 4, 6, 8, etc. Here in this plot, it is normalized to 2q squared over h, which is why it goes 1, 2, 3, and so on. So what this experiment then shows very clearly is it's like the basis for this whole viewpoint in a way. So one could say that, as I said, this whole viewpoint arose with the rise of mesoscopic physics back in the late 80s. And this was one of the very important seminal experiments, really, which gave solid grounds for this way of viewing transport, of viewing current flow in terms of this, the ballistic conductance being this q squared over h times the number of modes. Now one thing you might wonder is, well, why do I have to go to, say, small things to see this? Shouldn't you be able to see it even with much larger conductors? So for example, instead of going 1, 2, 3, etc., couldn't you be going, say, conductance versus width of a relatively large conductor, and couldn't you see something like this, where this may be, say, 997, that could be 998, that could be 999, and so on. And the answer is that, well, remember that the conductance we are calculating is at a given energy. So it is at this energy, let's say. And one of the points I had made earlier, something that I've usually, for clarity, not been writing explicitly, is the actual conductance is an average over energy. So in other words, we are talking about this conductance at a given energy, and the actual conductance would be obtained by averaging it over a certain range of energies, of the order of the voltage that is applied and the kT. And if, let's say at some energy it happens to be 997, another one it happens to be 998, another energy is 999, what that means is that at normal temperatures, when you measure this, you might actually get a fraction just because of that averaging, you see. And that is what would happen lots of times if you actually did this experiment at not very low temperatures. So this particular experiment, for example, was